we've got the basics of binary to decimal and decimal to binary encoding. One of the questions that often comes up is how big a number can you represent given a certain number of bits, right? You're trying to figure out, in a lot of cases, what's the smallest number of bits you can use to represent whatever value you're trying to encode. Do we need 16, 32, 64 bits, 128 bits? How big should we go? Because obviously the more bits you use, the more memory, the more disk space, whatever you're encoding is going to take up. Okay. So let's try and figure out a formula for how big can you get, right? Okay, and let's start small. So let's suppose we only had 2 bits to play around with. Okay, that's the ones place and the twos place. What is the largest number you could represent if you only had 2 bits? Well, it would be both of those bits turned on. So it would be a 1 plus a 2, which is 3. Okay, that's straightforward. Suppose I gave you 3 bits, right? What's the biggest number you could represent? So that's a 1 plus a 2 plus a 4 now. And so the biggest number you can represent is 7. And for 4 bits, 1 plus 2 plus 4 plus 8, 15. Right? It's the biggest number. Now there's a pattern here, but it might not be obvious, right? So there's a pattern here based on powers of 2. So 3 is actually 4 minus 1. And I chose those numbers because 4 is 2 to the second, right? So the biggest value you could represent with 2 bits is 2 to the second minus 1, 4 minus 1, which is 3. You can probably guess where this is going, but let me be explicit. 7 is 8 minus 1. Now 8 is 2 to the third, right? So the biggest number you can represent with 3 bits is 2 to the third minus 1, which is 8 minus 1, or 7. Okay, and so 15 is 2 to the fourth minus 1, right? So the biggest number you can represent with 4 bits is 2 to the fourth minus 1, which is 15. Okay, so the pattern seems to be, if I give you n bits, right, for whatever n is, 8, 16, 32, 64, whatever, right? The biggest number you can represent is going to be that 2 to the n minus 1, right? So for 8 bits, it's 2 to the 8th minus 1, which if you plug that into your trusted calculator, is 255. That's a number you might recognize from different contexts. For example, in a lot of file systems, the longest file name you can have is 255 characters, because that file system represents the file name length as an 8-bit value. Right? So yeah, 2 to the 8th, 255. Well, 2 to the 8th minus 1 is 255. The biggest number that you can represent with a single 8-bit byte is 255. Similarly, 16, right? It's going to be 2 to the 16th minus 1. Now, you definitely need a calculator for that one, unless you happen to have memorized that value is 65,535. Where do you see that value? That's the largest possible TCP or UDP port number, because TCP and UDP represent port numbers using a 16-bit value. Right? You can tell, actually, often from the maximum value allowed how something is represented internally in whatever data structure. So 32 bits, right? 32-bit computers aren't around much anymore, but IP addresses, IPv4 addresses are 32 bits, right? So what is the maximum number of possible IPv4 addresses? And the answer is a little over 4 billion. You may also recognize that number from certain older file systems and things like that that all use 32-bit addressing. So, 4 billion addresses seems like a lot, right? How is it that we ran out of IP addresses? Well, I mean, the answer is there's more than 4 billion devices in the world that need IP addresses, but actually, more to the point, the IP address space is sparse, right? We give people chunks of network to do with as they will, and they may not use all of that address space. Some of it's wasted, and that's part of the reason that we ran out of IP addresses and have switched to IPv6 networking, which uses 128-bit addressing, right? So remember, like, there's a huge differential between 32-bit address and 128 bits, right? It's 32 times 4 is 128, but moving from 32 to 128 bits is not like multiplying by 4 because it's exponential, right? So if I gave you 33 bits to play around with, you would be able to represent numbers up to double this value, over 8 billion, right? And so every extra exponent that I give you doubles the range of possible values. So the numbers get very big very, very quickly, each power of 2 you add. So 128-bit addressing lets you address an unbelievably large number of objects. So anyway, hopefully more than we'll need. So, okay. Now, here's the thing, though. The numbers we're talking about so far are all positive, right? An 8-bit byte lets you represent numbers from 0, to 255, okay? Cool. A 16-bit number allows you to represent numbers from 0 to 65,535. All good. But suppose I want to represent some negative numbers, right? That's a problem now for me. And so we came up with this encoding back in the day, decades and decades and decades ago, of how to represent negative values, right? Because binary doesn't care. Binary isn't signed. There isn't a way in a computer to tell the computer this is a negative number, okay? We need to encode negative numbers in a way that they can be manipulated. And so we created this notion called 2's complement notation. And the way 2's complement notation encodes negative values is to treat the first digit, the biggest digit, as a negative value. And then all of the other bits that follow are positive, and they are added to that negative value in order to create a range of numbers from negative to positive. Okay, so the computer doesn't know, right? It's up to the program to use the value as either what we call an unsigned value, which means that it's a range from 0 to whatever the maximum possible value is for that number of bits. That's what unsigned, and that's what we've been working with so far. Or if the programmer wants to use the value as what we call a signed value, where that first digit is treated as negative and all of the other bits are added to it. Okay. And so it's up to the application to use the numbers appropriately. Interestingly, at the very lowest level of the processor, it's completely unaware, right? It's just doing math to the bits. And the result of that mathing is effectively being done by the computer, ignorant of whether the numbers are positive or negative. It's just when the numbers do what we call overflow, that there's a different outcome if the numbers are negative versus positive. And that's very low level architectural stuff that you don't need to worry about. But it is interesting to know that this whole signed versus unsigned thing is entirely up to the application rather than being a feature of the low-lying hardware. So let's take an example here real quick. Okay. So here's our sample binary number again, 1011, right? Now, if what we did before is we were treating it as an unsigned value, right? So all the bits are positive here. So that's an 8021, right? Add them up like we did before, and you get 11. Okay, so the unsigned value associated with that 1011 number is 11, just like we saw before. But suppose we decided to treat this as a signed value. Okay, signed value means that this first digit, the eights place here, is treated as a negative number. And then all of these other places are positive, just like they were before. So we have a -8 here, because it's signed, and then a 2 and a 1. Add those together and you get -5. And so it matters, right? And you'll see in low-level programming languages, like when you're dealing with assembly language and things like that, or even C, I mean, you have to define whether it's signed or unsigned. For modern languages, Python, Java, things like that, this notion of signed versus unsigned is hidden from you. You just use numbers, and if they go negative, so be it. The programming language takes care of it for you. But in older programming languages, you actually had to specify, did you want to treat this as a signed or an unsigned value? And obviously it matters to you when you're trying to, decode these values. If you're just given a string of bits and nobody tells you whether it's signed or unsigned, you don't know how to treat that leading one, in your encoding. So let's do a few examples here. So I give you the 4-bit 0000. Now, unsigned or signed, it's always 0, right? I mean, there's nothing going on there. So that one's straightforward. But now let's try this one. Okay. So 1000. Remember that one leading one's in the eights place, right? So unsigned, it's an 8. Signed, it's a -8. Okay, let's get a little more complicated. 0010. Now, unsigned, that's 2. And signed, it's also 2. It's a trick question. Remember, the signed versus unsigned thing only really matters if that leading digit is set, right? If it's a 0 there, then it doesn't matter whether it's a signed or unsigned value, because all of the other bits are positive, right? So here we've got a number with no leading 1, so it's going to be the same unsigned or signed. Doesn't matter. And for example, here's another one, right? No leading 0. Okay, so unsigned, 4 + 2 + 1, that'd be a 7. And then that means that it's the same value signed as well. Oh, okay. Now it gets harder because we actually have that leading 1. So unsigned, let's see, 8 + 4 + 2, that'd be 14. Go me. But signed, we got a -8 + 4 + 2, right? So -8 + 6, basically, that'd be a -2. What happens when we turn on all the bits? Okay, so we've got -8 + 4 + 2 + 1. All right, 4 + 2 + 1, that would be 7. Okay, so -8 + 7 is minus 1, right? So it's 15 unsigned, and it's minus 1 signed. Now, this is a pattern I want to teach you, regardless of the number of bits, okay? If all the bits are turned on, then the unsigned value is going to be that maximum possible positive value that we talked about, 2 to the n minus 1, right? So it's going to be 15 unsigned. But signed, again, regardless of the number of bits, all ones signed is always going to be -1, no matter what, right? Because the sum of the trailing bits is always going to be equal to 1 less than the next bit up, the signed bit, basically. Okay. So if you had 32 bits all ones, it's still -1 as a signed value, right? And this is a value you frequently see. I mean, many functions return -1 as an error indicator. It's a value that crops up a lot when you're looking at data. So yeah, so all ones signed is always -1, regardless of whether it's 8 bits, 16 bits, 32 bits, 64 bits, whatever. It's always going to be -1. Wanted to point out a couple of other things. This number right here, 1000, okay, that is the most negative value that you can represent with 4 bits, because any other bits you turned on would make it less negative, because these are added to the -8. So 1 followed by all zeros is going to be the most negative value that you can have. And now is where we get to the mathematical trickery. So that is going to be, in this case, 2 to the 4 minus 1th power, right? Basically -2 to the 3rd. And keep that in the back of your brain for a minute, because we're going to look at another pattern, right? But if you think about it, basically the way this works is the biggest number you can represent is going to be, the most negative number you're going to represent is going to be whatever that leading place is as a negative number. Right? In this case, it's 4 bits, so that's -8. Okay, so -2 to the 4th minus 1, so -2 to the 3rd, right? We're going to use that in a minute. Now, going the other way, the biggest positive value you can have is everything 1 except for that leading digit, right? And in some sense, you can think of this like you instead of having a 4-bit number to play around with, you've now got a 3-bit number to play around with in the positive direction, because that leading digit would make you negative, okay? So for a signed value, the biggest possible value in this case would be 2 to the 3rd minus 1 instead of 2 to the 4th minus 1. Well, 2 to the 3rd is 2 to the 4 minus 1th power. You know what's coming here, right? I'm gonna teach you the formula for how to determine what is the largest possible value, depending on whether it's unsigned or signed. Now, unsigned, we actually already talked about, right? Given n bits, unsigned values range from 0 up to 2 to the n minus 1. Okay? We covered that one already. All right. What I'm telling you is that signed values range from -2 to the n minus 1th power to +2 to the n minus 1th power minus 1. And so you can, kind of make a little table for some of the common values, right? So 4 bits, we've been talking about, they range from 0 to 15, unsigned, right? That's 2 to the 4th minus 1. But signed, they range from negative 2 to the third, right? That's 4 minus 1, which is negative 8, all the way up to positive 2 to the third, right? 2 to the 4 minus 1. So that's 7. Okay. So that is the range we saw in the previous slide of possible signed values. And you can continue extending that formula out, right? We talked about 8-bit values range from 0 to 255. Okay. But for signed values, it's going to be negative 2 to the 7th up to 2 to the 7th minus 1. Similarly, 16-bit values, we talked about 0 to 65,535, like TCP and UDP port numbers. This is a number you might recognize, 32,767. You may have seen that pop up before in your computing career. That means you're dealing with a 16-bit signed value, right? So it ranges from negative 32,768 to positive 32,767. Examples of signed 16-bit values that you might run into. It's not coming to me. If you think of one, you can put it in the Discord. A lot of random number generators by default, like the random number generator in the Unix shell gives you a random number with a maximum value of 32,767. So we can tell it's being represented as a signed integer or signed short, really. 32-bit values, again, 0 to a little over 4 billion. But from a signed perspective, it ranges from, negative 2 billion and change to positive 2 billion and change. This one comes up because it's how times are represented in most Unix file systems. The 32-bit number represents the number of seconds since January 1st, 1970. We call it Unix epoch time. And it's a very common encoding for timestamps in Unix. By the way, there's actually a Y2K problem not too far ahead of us. With this encoding of time, we actually roll over in 2038. In January 2038, that 32-bit number of seconds value will overflow, and things are going to get interesting. Very interesting, because I believe that there will still be 32-bit computers operating at that time, just like we had old software in Y2K that only used 2-digit years. I plan on coming out of retirement in the mid to late 2030s and making a lot of money fixing those computers. But we'll see. We'll see how my retirement planning goes there. Okay. So numbers can be signed, which means they can range from negative to positive, or unsigned, and you need to know which one you're dealing with. So, next practice. Okay, so the next practice is, basically dealing with signed versus unsigned values. So here's 5, binary numbers. I want you to decode them as both unsigned and signed values. And then some questions about maxima, right? And my retirement plan. So see if you can figure out, I told you it was 2038, but see if you can confirm that by doing a little bit of math. Okay. For the other ones, again, I just wanted to point out, the leading one, and then all zeros. It's either going to be 128, right, unsigned, or negative 128 signed. Similarly, again, what I said for all ones, right? Unsigned, it's 2 to the n minus 1, right? So 2 to the 8th minus 1, so 255. For signed, though, all ones is always negative 1. And that's a pattern you can use regardless of the number of bits in your number. And then these numbers are what they are. I mean, you can do it by hand, once or twice, but eventually you're going to put them into a calculator. Okay, let's talk about some of these other questions. The word problems. My kid hates word problems. All right, so IPv6 uses 128-bit addressing. That's a big number, right? The maximum number of unique IP addresses is going to be 2 to the 128th minus 1. I mean, I plug that into a calculator. I'm obviously not going to calculate that by hand. And the answer was something greater than 3.4 times 10 to the 38th unique addresses. That is a really big number, right? That's a 3 with 38 zeros after it. I don't even know what that number is, right? But it's billions upon billions upon billions upon billions. So we should be good as far as address space goes with IPv6. I mean, that was the intention, right? Is to pick a size that we should never run out. I mean, never say never, but that is a big number. Now, this DOS partition table thing is a little bit tricky for people. Okay, so 32-bit number of sectors in the partition, basically the partition length. So what's the maximum number of sectors? Well, it's going to be 2 to the 32 minus 1, which is that 4 billion value you see right here, right? 4,294,967,295 sectors. Okay. Now, if each sector is 512 bytes, when you multiply that out, right, it's basically, it's 512 times this number. Now, the way I think about it, because I've been looking at these partition tables for forever, right? 512 bytes is half a kilobyte, right? So 2 sectors is 1K. So if we divide this large number in half, so 2 billion and change, you'll have the number of kilobytes, right, in the partition. Right? And then, so this number of kilobytes is actually 2 terabytes. And I mean real terabytes, not, hard disk manufacturer terabytes where they're only multiplying by 1,000. I mean real terabytes where you're multiplying by powers of 2. So the maximum partition size you can have with an old DOS style partition table is 2 terabytes. And you may have run into this limit, when you're back in the day when you got your first, 4 terabyte hard drive. For a while there, the biggest partition you could specify was only 2 terabytes. And so you'd have to make multiple partitions to fill up your disk. How did we fix that? We went to a different partition tabling scheme, as it turns out. Modern computers use this thing called GPT, GUID partition tables. And GPT uses 128-bit addressing. So again, way more sectors than you would ever possibly have. Although at the rate hard drives are growing, you never know. But anyway, so that's where that old 2 terabyte limit came from, if you were ever wondering. You can only specify about 4 billion sectors, and when you map that out in terms of bytes per sector, you end up with about 2 terabytes. Now, my retirement planning. I claimed that the 32-bit signed integer dates were going to roll over in 2038, okay? How did I get there? Okay, so 32-bit signed integer, right? The maximum number of seconds you can have is 2 billion and change. Okay. There's 86,400 seconds per day, right? 60 seconds per minute, 60 minutes per hour, 24 hours per day. When you multiply 60 times 60 times 24, it ends up as 86400. Okay. 86,400 seconds per day times 365 days per year. I'm ignoring leap years, leap seconds, and all of that stuff. We're just doing quick back of the envelope calculations. Okay. When you divide the maximum possible seconds value by this number, you get a maximum of 68 years. Ignore the rounding error. Okay, cool. So if the epoch starts at 1970 and you have a maximum possible spread of 68 years, that means we're going to run out in 2038. In fact, it's in the middle of January in 2038. So you better have your ducks in a row before the end of 2037, because you're not going to have much time to fix this problem. And yeah, this is a real thing that's going to happen, I believe, because people are going to not realize that they have, old legacy systems that are still using 32-bit dates, and it's going to be a bit of a scramble. We actually have a question coming up in a little bit that talks a little bit about how Unix file systems are working to fix this problem ahead of 2038. But I guarantee you there will be 32-bit systems that need fixing in the mid-2030s. I will be 70 years old in 2038, and but I plan to come out of retirement and like the old mainframe programmers did for Y2K. Yeah, I'm going to be that annoying old Unix programmer who comes out of retirement and tells you kids to get off my lawn and stuff like that. Anyway, so here we are. That is the mathing on all of this.